Welcome to the lecture on electrical circuit analysis. So, our today lecture is on first and second order circuits. So, the learning objectives of this today lecture is to define what is meant by first order and second order circuits, and to define the natural and step response of a circuit, and the third objective of this lecture is to determine the natural response of a given RL circuit, and the last one is to understand the switching times of the transient switching times of the any given circuit. So, how to understand the switching time, and when the switch is closed, which is opening, before opening the switch, before closing the switch, after opening the switch, after closing the switch. So, various conditions how we are going to calculate, we are going to discuss in this lecture. Okay. First order circuits. So, a circuit that contains only one source, resistor and an inductor is called first order RL circuit. Is called RL circuit. If the circuit contains only source, resistor and capacitor, then it is called a RC circuit. Okay. So, this RL and R circuits are called first order circuits because their voltages and currents are described by first order differential equations. First order differential equations. Now, if you see the RL circuit, now this is the an RL circuit, okay, which consisting of voltage source, resistor and inductor. Okay. So, this is RL circuit. Now, this is our RC circuit. Okay. Source, voltage, resistor and capacitor. Now, when you apply the Kirchhoff voltage law or Kirchhoff current law in the circuits, so we are going to obtain the first order differential equations. Now, see, if you apply the Kirchhoff voltage law in the first two circuit, that is RL circuit. So, what is the KVL? So, Vs is equal to R into I plus L into di by dt. So, voltage across inductor formula is L into di by dt. This L into di by dt, this di by dt is a first order term. Therefore, this circuit we are calling as a first order circuit. And if you apply the current flowing through the capacitor, so I is equal to C into dV by dt. So, current flowing through the capacitor formula, I is equal to C into dV by dt, dVc by dt. So, dVc by dt is the first order term. Therefore, this circuit is also first order circuit. That means, if the given circuit contains one energy storage element, then the circuit is called first order circuit. If the given circuit consisting of two energy storage elements, then the circuit we are calling as a second order circuit. So, first order energy storage element means, so inductor and capacitor both are energy storage elements, because inductor stores the energy in the form of magnetic field, whereas the capacitor stores the energy in the form of electric field. Therefore, inductor and capacitor are said to be energy storage elements. So, therefore, if there is any circuit containing inductor or capacitor, so if it is only one inductor, then it is a first order circuit. If only one capacitor, that is a first order circuit. If the circuit contains two inductors, then it is a first order circuit. Two capacitors, then it is a second order circuit. That means, if the circuit contains two inductors, then it is second order circuit. If the circuit contains two capacitors, then it is second order circuit. If the circuit contains one inductor, one capacitor, then it is also a second order circuit, because two energy storage elements. Okay. So, this is what the definition of the first order and second order circuits. Okay. So, let us review. So, any first order circuit can be reduced to a Thevenin equivalent circuit or its equivalent Norton equivalent circuit connected to either single equivalent inductor or capacitor. Okay. Now, see here, now if you see the circuit, so okay, so this is what current source, that is I Nortons, and parallel with the resistance, so R Nortons across the inductor L. So, this is what Norton equivalent circuit for any given network. Now, this is the Thevenin equivalent circuit for any given circuit. So, V Thevenins in series with the R Thevenins across the capacitor C. Therefore, we know that in steady state condition, so inductor acts as short circuit and capacitor acts as open circuit for DC. So, we know the properties of the inductor and capacitors. So, as the inductor does not allow the sudden change in the current, therefore, it acts as a short circuit for DC, in the steady state condition, and the capacitor property is the capacitor does not allow the sudden change in the voltages. So, therefore, the capacitor acts as a open circuit for DC in a steady state condition. So, these are the points you have to remember the properties of inductor and capacitor. Why? Because if without this, so there must be infinite voltage must be there in the inductor, and infinite amount of current must be flowed in the capacitor. So, which is not possible practically. Okay. So, that is what the concept of this inductor and capacitor properties and first order RL and RC circuits. Now, what is meant by a natural response? So, the natural response of an RL and RC circuit is its behavior when stored energy in the inductor capacitor is released to the resistive part of the network. Otherwise, you can also say that whenever this RL and R circuit, the response of the RL and R circuit when the switching action, the immediately after the switching action. So, that means during the switch on condition, the inductor capacitor store the energy. So, when once the switch is off, the inductor or capacitor stored energy must be released in the resistive part. So, what is the response during that switching action? We are calling as a natural response of an RL and RC circuit. So, response means what? Whether you have to find the voltage across the inductor or current flowing through the capacitor, whatever it may be. So, the natural response of an RL and RC circuit is its behavior when stored energy in the inductor capacitor is released to the resistive part of the network. So, which containing the no independent sources. Now, what is meant by step response? The step response of an RL and RC circuit is its behavior when voltage or current source step is applied to be a circuit or immediately after a switching state is changed, that is switching opening, switch closing. Immediately when the switch is opening, what is the response? That is the step response. Immediately after switch is closing, what is the response? That is called step response. Okay. So, this is what the natural response and step response definition. Okay. Now, let us find the natural response of an RL circuit. Let us find the natural response of the RL circuit. RL circuit. Okay. So, consider the following circuit for which switch is closed pole. Now, see here. Now, in this circuit, at t equal to 0, the switch is opening. At t equal to 0, switch is opening means at t less than 0, that means before opening the switch is, you have to assume that on condition, which is closed condition. Switch was in closed condition at t less than 0, but at t equal to 0, switch is opening. Okay. What is the response? So, here the DC voltage V has been supplying the RL circuit with constant current R for a long time. Now, see, when the switch is closed, okay, when the switch is closed, this DC current source is supplying the current to this for this RL circuit. Okay. So, for t less than or equal to 0, okay, now whenever this switch is closed for t less than 0, so the current flowing through the inductor, let us say, we do not know that, let us say I naught, we do not know that, that is I naught. Therefore, I of t is equal to what? I naught. Now, for t greater than or equal to 0, that means the circuit reduces. That means when the t greater than or equal to 0 means switch is opening. When the switch is opening, now this is circuit now. This is our circuit. Okay. So, this is our circuit. That means switch is opening means what? So, it is opening. Now, here you have to understand the switching timing is like this. T equal to 0 means switching opening or closing. In this example problem, t equal to 0, switch is opening. So, t equal to 0 minus is used to denote the time just prior to switching. That means time just to before opening. Time just before opening in the circuit. T equal to 0 plus is used to denote the time immediately after switching. It means in this circuit, t equal to 0 plus means the time immediately after opening the switch. So, in this example problem, t equal to 0 minus means when the switch was in closed condition, t equal to 0 plus means immediately after switch is opening, t equal to 0 means the moment at which switch is open. So, this is what the three conditions. Okay. T equal to 0, T equal to 0 minus, T equal to 0 plus. Now, to find out the response, we have to apply the Kirchhoff current law. Kirchhoff current law. So, V of t plus R into I of t. Okay. So, V of t plus R into I of t. Now, you apply the Kirchhoff voltage law in this loop. Okay. So, what is the voltage across the inductor? L into di by dt plus R into I. So, this is what is second equation. So, L into di by dt plus R into I of t is equal to 0, equation number 2. Now, what we have to find? We have to find out the current I of t we have to find. Therefore, you do some mathematical operations. You bring this L to the RHS side. Okay, first you bring this R to I of t to the RHS side, then you will become, you will get the equation 3, that is L into di by dt, di of t by dt is equal to minus R into I of t. Now, in the next step, you bring this L to the RHS side, therefore, what you will get? So, di of t by dt is equal to minus R by L into dt. Now, I want to find out the, what is what? So, I of t. So, how will you get it? So, if you integrate on both sides, differentiation integration will get cancelled. Therefore, you can easily solve the I of t. So, from the equation, we know that integral formulas du by u equal to minus R by L into dv. Okay. So, integrate on both sides of the equation 5, then you will get, so see this here applied the limits here, upper limit and lower limit. So, lower limit is I into t naught, I of t naught, and that is the immediate the switching action, and I of t, that is the final condition. So, du by du equal to minus R by L into integral of t naught to t into dv, equation number 6. So, where I of t naught is the current corresponding to a time t naught, and I of t is the current corresponding to time t. See, if you want to apply this I of t naught and that is the limits for the integral, you can apply. Otherwise, after integrating, you will get a constant, that is called k, integral constant. Once you get the integral constant, you can also solve this integral constant by applying the initial conditions. That means, before opening the switch, what was the current flowing through the inductor. So, by that, using the initial conditions also, you can easily find out the integral constants. Otherwise, you can also apply the limits of the limits for the integration, integral limits. Therefore, so 1 by x into dx is log x. Therefore, ln I of t I naught, so I is equal to R by minus R by into t, because integral of 1 dt is t. Okay. Therefore, you will get here I of t is equal to, I of t is equal to I naught into e to the power of minus R by L into t, that is equal to I naught into e to the power of, what is I of t? So, I of 0 is equal to what? As initial condition, this I of t is equal to I naught. So, substitute in this equation. Therefore, you will get here I naught into e to the power of minus R by L into t. So, this is the natural response of a RL circuit. That means, once the switch is opening, so the energy stored by the inductor has to be dissipated in the resistor. That means, the inductor's current is decreasing exponentially. The inductor current is this. What is this? E to the power of minus R by L into t. This minus indicates the current is decreasing exponentially. So, this can also be written as in the form of the time constants, the term called time constant tau. Okay. Now, once you get the current response, so it is easy to find out the voltage. So, voltage across the, what is the voltage across the resistor? What is the voltage across the inductor? So, from the Ohm's law, we know that the voltage across the resistor R is V of t is equal to I into R, that is I of t into R. So, already we got I of t is I naught into e to the power of minus R by L into t multiplied with R, you will get the voltage across the resistor. Once you get the voltage across the resistor, then it is easy to find out the power absorbed by the resistor, that is P is equal to product of voltage into current. So, V of t into I of t. So, V into, so what is V? V of t we got just now, I naught into R into e to the power of minus R by into t into I of t is what? I naught into R into e to the power of minus R by L into t. Therefore, you will get I naught square R into e to the power of minus R by L into t. Okay. So, this is what the condition. So, therefore, once we get the power, then it is easy to calculate the energy absorbed by the resistor of Li square. So, half into 1 by 2 into L into I naught square into 1 minus e to the power of minus 2 into R by L into t. Now, this current equation I of t, okay, and voltage equation V of t, okay, and the power equation. So, these all are can be expressed in a time constant form. So, what is this time constant? So, time constant tau determines the rate at which the current or voltage approaches to 0. That means, see here, now we obtain the current is I naught into the power of minus r by L into t. Okay. From this expression, I can say that current is decreasing exponentially. Okay, it is decreasing to 0. Okay, so how much time it will take to decrease the current to 0? So, which depends upon the time constant of the circuit. So, the time constant here minus r by L, that is time constant is defined as it is a ratio of inductance by resistance. So, denoted by tau, it is the ratio of inductance by resistance. The units for time constant is seconds, L by R. So, therefore, here now see this current equation I naught is equal to I of t is equal to I naught into the power of minus r by L into t. Now, you bring this r to the denominator. Okay. So, you can get you can write one r is a L by R. Okay, L by R. Therefore, you will get like this. So, this is what the expression. So, I of t is equal to what? So, I of t is equal to I naught into e to the power of minus t by tau, where tau is equal to what? L by R. Now, substitute here tau is equal to L by R. So, R will go to the numerator. Therefore, minus r by L into t, same. Now, V of t is equal to I naught into R into the power of minus t by tau. What is the importance of this tau means time constant is at what rate the current is decreasing or voltage is approaching to 0. That is called the time constant. So, that means the rate at which the current or voltage approaches to 0 we are calling as a time constant. So, it is denoted by tau and it is given by for RL circuit L by R. So, that means the rate is depending upon the inductance and resistance of the circuit, given circuit for RL circuit. Now, power is equal to what? So, 1 by 2 into power is equal to I naught square into R into the power of minus 2 t by tau. Okay. So, it is in the form of time constant form, voltage, current and power and energy. So, energy or W is equal to 1 by 2 integral of 1 by 2 into L into I naught square into 1 minus e to the power of minus 2 t by tau. Okay. Now, coming to the switching time. So, for all transient cases, so transient cases means whenever the switch is opening, whenever the switch is closing. So, immediately the response we are calling as a transient response. Okay. For all transient cases, we have to consider some times. See, just now I discussed. So, again I am explaining here, t equal to 0 minus means this is the time of switching between minus infinity to the 0. So, t equal to 0 plus means this is the time of switching at the instant just after t equal to 0. This is taken as initial value. T equal to 0 plus means initial value. And t equal to infinity means this is the time of switching between t equal to 0 plus to t equal to infinity plus infinity. That is a final value. Final value. So, this is what the illustration of the different instant of switching time. See here, t equal to 0 minus. Okay. So, t equal to minus infinity to 0. Okay. Minus infinity to 0. So, minus infinity to 0 is t equal to 0 minus. Okay. And it is a t equal to 0 to plus infinity. It is a final value after switching action. Okay. So, this is what the today lecture is on first order and second order circuits. What is the current flowing through the resistor RL circuit? I of t is equal to I naught into e to the power of minus t by tau, where tau is equal to time constant, that is tau is equal to L by R. It is in measured in seconds. Okay. So, thank you for listening in the class. We will join in the next class. Thank you.